fragments, the heavy fission fragments. And superimposed on this is actually a possible R process path. So these are the nuclei most likely to be formed in the R process. And you can see that we have been able to study nuclei on the R process as well as very close to the R process with this wonderful facility at Oak Ridge. What I'm going to focus on today are our studies near tin-132, so the N equal 82 isotones, but more importantly, many of the isotopes that are neutron-rich in tin. We've done both neutron transfer DP reactions as well as what seems like a very exotic reaction, beryllium-9, beryllium-8. Elizabeth Padilla in the next talk will talk a lot more about those studies, where we're able to measure Q values, single neutron excitations, spectroscopic strengths, and we can use particle gamma coincidences to give us better measures of the excitation energies, help confirm spin parity assignments, as well as populate states that would not have been populated directly in a selective reaction such as DP. And I will spend the last part of my talk talking about how we actually are starting to use these data to help inform neutron capture rates on exotic nuclei, in particular important for our process, for example. The work that I'm talking about today is a collaboration of Rutgers University, Oak Ridge National Laboratory, University of Tennessee, Tennessee Tech, Michigan State University are the key people, as well as people from Boral, Louisiana State, Surrey, Colorado School of Mines, Ohio University, and UNAM. Most of the data that I'll be talking about were taken by Kate Jones, who was my former postdoc. Very important data, which are right now finalizing by Ray Koju, and more recent work by my student Brett Manning and, of course, Steve Payne. Many of the theoretical reaction calculations were done by Philomena Nunes. And so this is just to orient you. I asked a question of Rick earlier today, how far away from stability do you have to go? Well, we started off 8 units away from stability with beams of tin-132. Tin-132 only lives for 40 seconds, but we've been able to do beautiful nuclear reaction and structure studies with that beam. What we expect to see, this is the N equal 82 gap, so we're expecting to populate orbitals above the gap, and in particular with a neutron transfer reaction like DP, we're going to be predominantly populating L equal 1 and L equal 3 transitions. These are actually our data. So we're doing reactions in inverse kinematics with a beam of tin-132, which is about 5 million electron volts per nucleon. So that's traveling at about 10% the speed of light. And so everything is done, it's not quite relativistic, but you have to take into account inverse kinematics. And so our proton energies change as a function of angle with kinematic curves. The ground state, first excited state, and a 5 hats minus state were previously known, but you can see there's extra data here, which we interpret to be the missing 1 half minus state. In my next slide, I will take these data, which are in the laboratory frame, and convert them to center of mass energies. So this is, again, the ground state, the first excited state, the 5 hats minus state, which was previously seen in beta decay, and our new 1 half candidate for the 1 half minus state. Important in understanding our data are to measure the intensities of the protons as a function of angle to get cross-sections and angular distributions of cross-sections. We do 2 kinds of measurements. One is we actually look at the elastic scattering of the reaction deuterons for normalization, and then we actually calculate the angular distributions of the protons as a function of center of mass angle. Our initial calculations were done in the traditional distorted wave Born approximation, where we have optical model potentials, which we have to use for the deuteron incoming, the outgoing proton, the bound state of the neutron. We also take into account the wave function of the deuteron, And in more recent calculations, we've actually taken into account the breakup of the deuteron as well as the wave function of the transferred particle. What we get from this is a spectroscopic factor, which the most simple way to do it is you take all of your theoretical calculations, which includes a single particle wave function for the transferred particle, and we compare that to experiment. If s is equal to 1, then our wave function for the transferred particle is pure, i.e. we have all, for example, the F7 half strength. If it's less than 1, it's fragmented. If it's greater than 1, it's unphysical, because you can only have all of the strength. You can't have more than all of the strength. So these are now our angular distribution. Cross-sections is a function of center of mass angle for the ground state, which was previously identified to be a 7 halves minus state. And you can see that the angular distributions are consistent with the red curve, which is 2F7 halves transfer. And by normalizing the calculations to the data, you get a spectroscopic factor. And the spectroscopic factor is very close to 1.86. The first excited state had also previously been seen in beta decay and fission fragment studies. It had been proposed to be 3 halves minus. And now the dotted curve is for P3 halves transfer, and again with the spectroscopic factor very close to 1. The 5 halves minus state, there is a candidate for the 5 halves minus state of 2 MeV. This is unlikely to be a low spin state because of the selection rules from the previous fission fragment and beta decay studies. We unfortunately were unable to get an angular distribution, but normalizing the calculations to the data point, we can get a spectroscopic factor of essentially 1 for F5 halves transfer, but it would have been greater than 1 if it was the missing P1 half. But as I said, it was expected from previous work, this should not have been a 1 half minus state. And that leaves this new state at 1.36 MeV. Again, we could not get an angular distribution, but normalizing the calculations to the one data point of cross-section, we get, again, a P half strength that's very close to 1. We couldn't naively eliminate the F5 halves, but we have already identified all of the F5 half strength in the state at 2 MeV. And so to summarize these results, we have identified candidates for all of the L equal 1 and L equal 3 excitations above the N equal 82 shell gap. We have spectroscopic factors, which are consistent with 1. We have recently done finite range adiabatic wave calculations where we've taken into account the deuteron breakup, as well as finite range, and those spectroscopic factors